G'day guys, we've got a calculus question today where it's asking us to calculate an integral and to make sure that we show our full working out. So basically what it's saying is we can't go to a calculator that has integration facilities on it. We need to do this thing by hand. Now the complicated part about this question is to start with, to be able to integrate this, we need to get this fraction as an addition of two fractions with linear denominators rather than a quadratic that we see here. And so the way that we do that is we're going to split this 1 over x squared plus 5x plus 6 into two partial fractions and then integrate those partial fractions separately. And that's the method that we're going to use today to calculate this particular derivative. Okay, so to start with, what we have to do is we have to find the factors of the denominator, and I might do the partial fractions part over here. So what we can say is we're going to say that 1 over this quadratic is equal to, now the factors of this denominator are going to be x plus 2, x plus 3. So we're just going to go x plus 2, x plus 3. Now, we've still got our 1 over the top. Now, what we're going to do, the way that this is going to work in terms of our partial fractions, is we've got to redo the numerator so that we can break the denominator into two linear sections, i.e. x plus 1, or x plus 1, x plus 2 and x plus 3. So what I mean by that is we're going to then make this equal to a, now this is the partial fractions part, over x plus 2, and we're going to add that to b, which is x plus 3. Now the reason I do this is so I can then separate them in the end. So I need to find out what a and b equal. So what I'm going to do is I'm going to then recombine the fractions and then try and bring this relationship or this equation here back to looking like this so I can equate the two numerators. So what I'm going to do is I'm going to say, well, this is equal to, if I put them back together like this, if I just have x plus 2 and x plus 3 in the denominator, what I can do is to get this fraction to look like this, I have to multiply top and bottom by x plus 3. So I'm going to have a times x plus 3. Then to that I'm going to add, to get this fraction to look like this, I have to multiply both numerator and denominator by x plus 2. Cool. So what I'm going to do now is I'm going to multiply out those brackets. And I have ax plus 3a plus bx plus 2b all over x plus 2, x plus 3. Great. Now what I'm going to do now is I'm going to regroup my numerator so I have the x's together so I can factorize them. So I'm going to factorize the x's. So that's going to be, they both share a common factor of xa plus b times x. So I've factorized this part and this part. And then I'm going to that I will add plus 3a plus 2b. And that's all divided by x plus 2, x plus 3. Cool. So what we can do now is we've got to use a little bit of mathematical intuition, and we say that, well, in our original fraction, we just have the number 1 in the numerator. So what we know is, well, because there is no x in the numerator to start with, we know that a plus b, because that will be the coefficient out the front of the x term, that will have to be equal to 0. So from here, what we're going to say is that a plus b will equal 0. And from that, we can say that a is going to have to equal negative b, or the opposite of b, because we can move the b over the other side. And what we also can say is, because the 3a and the 2b, when combined together, they're going to produce the single number 1 that we have in our numerator. So we can say that 3a plus 2b must equal 1. What we can do is we can substitute for a, and we can say that 3, and rather than write a, we can write negative b plus 2b is going to equal 1. Negative 3b plus 2b is just negative b, has to equal 1. So b is going to equal negative 1. And because a is equal to the opposite of b, a is just going to be equal to 1. So what we can say now is taking the integral of this is going to be, well, I'm going to do this all in long form, so I can say that 1 over x squared plus 5x plus 6 is equal to 1 over x plus 2 minus 1 over x plus 3. So, because these two things are equivalent, that's what we've spent all this time doing, is trying to get the quadratic in the original fraction, denominator, into two linear equations, which we have now. So, what we're going to do is now we can take some integrals. So we can say that rather than saying what is the integral of 1 over x squared plus 5x plus 6, we can say, well, this is going, well, we can also find the integral of 1 over x plus 2 minus 1 over x plus 3. So these two statements are equivalent, except for the fact that this is an indefinite integral. So from there, we can actually just calculate the integral. So from here, what we can do is we can go, well, because if we have the integral of fx plus or minus gx, this is going to be the integral of fx plus or minus the integral of gx. So we can say that this is the integral of 1 over x plus 2 dx. Take the integral of 1 over x plus 3 dx. So then we can actually start doing some integration. So we know that hopefully you guys know that the integral of 1 over x plus 2 is equal to the natural log of the absolute value of x plus 2. And that's going to be subtracted, and we have the natural log of the absolute value of x plus 3, because the integral of 1 on x dx is equal to ln of the absolute value of x plus c. So that's all, we plus a constant term. So then what we're going to do is from here, we're going to just evaluate it at our limits at 0 and 1. So we obviously start from, we evaluate it at 1 and we subtract us evaluating it at 0. So we can just, let's work with this one. We're going to evaluate this between 0 and 1. And that's equal to, well, at 1, we've got the ln of 3, subtract the natural log of 4. Put that in another bracket, just so we can separate it out. Minus the natural log of 2, minus the natural log of 3. Cool. So what we're going to do is we're going to simplify this a little bit. I'm going to, well, this one here, we've got ln of 3 minus ln of 3, so that's plus. So this is going to be equal to 2ln of 3. So that's with using this bit and that bit, we can tick that off. Now ln of 4, this piece here is the same as saying minus 2 ln of 2, because 4 is 2 squared, and we can then take the index out the front. So what we can do now is we've got negative 2 ln 2, take ln 2, is going to be take 3 ln 2. Now from here, so we're basically finished now, what we can say is this is going to be the same as saying ln of 3 squared, which is 9, subtract ln of 2 cubed, which is 8. Which, using one of our logarithmic laws, we can say this is equal to the natural log of 9 divided by 8 units squared. Cool. So that's our answer right there. Let's just make it nice and easy to see. So what we had to do here, guys, is the reason why we had to use these partial fractions is because we had a quadratic function in the denominator of this integral. What we had to do is we had to use the method of partial fractions to separate the quadratic denominator into 2 linear factors and then make an equivalent statement. So 2 linear denominators, which when added or subtracted by each other, made this particular function here, rational function. What we then did is, because once we found the linear denominators, we were then able to break the integral up and say, well, this is going to be the integral of this part plus the integral of, or in our case, minus the integral of this part, which made the problem quite easy to compute when we went down and through all of our log laws to solve it. So, there are a few bits of prerequisite knowledge to, so follow me on this question. One is that you understand how all the log laws work, and the other is that you have a sort of a brief understanding how the method of partial fractions works. If you don't, what I would suggest is you just go watch a video on this method of partial fractions, then come back to this one, just so you can sort of better understand why I'm doing this one. But other than that, guys, again, it's just noticing that this is what we have to do with this question. The quadratic denominator is a red flag for me that we need to use partial fractions. But, again, practice, practice, practice. It makes perfect. All we have to do is just keep on getting more problems and trying to solve them. If you have any problems, though, with any of the problems you're trying to solve, if you're hitting any brick walls, don't hesitate to sort of leave a comment in below, and I'd be happy to try and answer it. But until next time, guys, keep working and enjoy your maths.